Okay, after the analysis of application requirement, we have to figure out the features of our DMA controller. How to make a DMA controller that will ease the application of 2D games. So here, I list some of the key features for our DMA controller. The first is we need to have a DMA controller that can copy data of 2D window. This is because the data layout for the pictures is two-dimensional. For example, this is the map. When we store the pixel values of the map in a system address, it's usually in the format of raster scan. That is from left to right, then from top to down, line by line. So this is usually the data layout in system memory. It's usually in the raster scan format. When we want to cut some parts of this figure, for example, if we just want to show this part, then you can see this is the data of 2D window. Yes. And the address for the pixel value in a line is consecutive. The address of the pixels in this line is consecutive. And there will be a address gap between each line. So this is the gap between each line. Then you will copy pixels of next line. And this will repeat line by line. So you can see the address for the pictures itself is two-dimensional. So we have to design a two-dimensional DMA controller. And the source and destination address can start from any byte location. No need 32-bit aligned. This is for flexibility. Typically, the address space taken by a pixel is around 1 byte to 3 bytes. So if it's a grayscale frame, there is just 1 byte for each pixel, and if it's in RGB format, each color component will have 8 bits. So 1 pixel will take up 3 bytes. And also there may be RGB 565 format. Then the 3 component will take 16 bits. That is 2 bytes. So usually a pixel will take 3 bytes to 1 byte. If we want to show the frame in this range, so you can see so the start address for each line will be in any byte number, maybe 1, 2, 3, 4, 5, 6, any byte number. So we have to make sure our DMA controller supports source and destination address start from any byte location. And we limited the byte length in a line to the range of bigger or equal to 4 bytes and smaller or equal to 65,536 bytes. That is 16th power of 2. So we will use counter of 16 bits to count for this value. This number is chosen to meet most of the applications. For example, if we want to copy data of 1920 pixels multiply 1080 pixels. So you can say the byte number within a line should be, yes. So this is smaller than 16th power of 2. So we can just use one DMA command to copy all the data in this window. If you want to copy bigger frames, such as up to then you can figure it out. It's also smaller than 16th power of 2. So we can also use just one DMA command to copy all the data in this window. And if even bigger, this will exceed the range of X size. So how to deal with this situation? In this case, you can divide it to 2 or 3 DMA commands. For example, first you can just copy frames within this window. Then next, copy data within this window. Then third, copy data within this window. And last, use the fourth command to copy data of this window. Yes. Okay. Also, we limited the value range for lines within a 2D window to the range of bigger or equal than 1 and smaller or equal to 16th power of 2. As we have showed before, there can be any byte number of gaps between each lines. And the gap for source and destination can be different. For example, in this figure, this is the address layout for the source data, and this is the address layout for destination data. You can see here, this is the gap between each line. We name it as source address Y step, and this is the gap between each line and destination. We name it as destination address Y step. So the two can be different values. And we need to support the scatter gather mode. That is, for each trigger, we can copy many 2D windows. And in this design, we limited the number of windows to 255. If you think there is more objects within a frame, you can increase this number. And we will use some advanced features in AXI bus protocol to improve the bound width. For example, we will implement the read command outstanding read data out of order functions provided by AXI bus protocol, and the concurrence of read-write channel on DMA interface. That is, the read and write burst can happen at the same cycle. This is because the data throughput for our application may be very high. For example, you can figure out if you want to copy a figure of this resolution, and we assume each pixel is 3 bytes, we will achieve the frame rate of 60 15 frames per second. You can calculate the bandwidth we needed. This is this number multiply this number multiply 3 and multiply 16. So this is the result. This number should be about 373 megabyte per second. That is, this block will read and write out data of 373 megabyte. This is somewhat a big number for the bus system, and we have to utilize the advanced features of AXI bus protocol to improve the data bandwidth. Okay, this is the key features of this block. And you can see, with these key features, you can completely replace the CPU routing memory copy. And our features is a superset of memory copy. Memory copy can just handle data of one dimensional. Okay, here is a question for you. If we just define a one-dimensional DMA controller, it can also copy data of 2D window. Yes, you can use command list to copy data of 2D window. For example, you will use one command to copy this line from here to there, and the next DMA command to copy this line from here to there, and the fourth DMA command to copy the 4 lines. So you have to use one command for each pixel lines. You can also make the function of copy data of 2D window of a picture. So what's the benefit? What's the benefit of 2D DMA controller over 1D DMA controller? What's the benefit? You can imagine the hardware design for this should be a little complex over this one. And what's the benefit we will get from 2D DMA controller? Please think about it. Okay, this is the block diagram for this block. Clock reset, then we use APB protocol to configure registers inside this block, and we use AXI master interface to read and write data. After each trigger by software, the controller will process all the DMA command in the command list. After all the command has been finished, it may give an interrupt to CPU core, and the CPU can read the status of this command. If it wants to copy data of next block, it can configure the next command list and trigger the controller again. If this block is integrated in a SoC system, it may be in the place as shown in this figure. This is the DMA controller, and this is the AXI interface, and this is the APB interface. This is the AXI interconnect. So when CPU wants to copy some data, it first configures the DMA information to DMA, or store the information in some other space, such as the HRAM or the DDR space. Then it will trigger the DMA to work. CPU can read-write configure registers inside the DMA controller through APB interface. Usually, it will use this data path. First, there will be a read-write transfer on the I/O of CPU. Then, it will pass to the interconnect, and the interconnect will decode this transfer to this bridge. This bridge will change the AXI protocol to APB protocol and select this slave. So the read-write transfer and the I/O of CPU can pass to the APB interface and the DMA through this path. After the trigger of DMA controller by CPU core, the DMA will read and write data through the AXI interface. So first, it may read data from this address space and write to this address space. So this is the place for this block inside a SOC system. Okay, this is the key features and the block diagram of this block. So if we want to copy a data of 2D window, how to describe this DMA information? To describe the characters of a 2D window, you must have the source start address. Yes, so we limit it as SAR, and also you need to have the destination start address. We limit as the DAR, and also the byte number within a line. This is X size, and the number of lines of this window we limit as Y size. If Y size equal to 1, it will degrade to traditional 1D DMA. And we have to define the byte number gap between each line and source address space. So we limit as SA Y step. That is this address space in this figure. Also, we have to define the byte number gap between each line and destination address space. We limit as DA Y step. So that is this address space in this figure. By using the 6 variables, we can fully describe the data movement of a 2-dimensional window. And in this figure, if we set SAY step to 0 and DAY step not equal to 0, it can scatter data. That is, it can copy data from continuous address space to discontinuous address space. And if we set SAY step to non-zero value and DAY step to 0, then it can gather data. That is, it can copy data from discontinuous address space to continuous address space. For example, if we want to copy the pixels in this range, and form a new picture, so there is a gap between pixels in each line and source address, but there is no gap between each line and destination address. Okay. Next, let's figure out how to support command linked list. So to support this, we have to define a register slash code it as linked list register. So besides the 6 variables we used to describe the characters of a 2D window, the 6 variables we have defined here, we have to add another register named as linked list register. This register will point to the begin address of next DMA command. And how to define the end of this linked list? In our design, we use the special value of 0. If the value for this register is 0, we treat it as the end of the command list. For example, if this is the last command for this trigger, you have to set the value of this register slash to 0. So when the controller gets the information of this DMA command and it finds that the LLR is equal to 0, then it gets the idea that this is the last command for this trigger. After the finish of this command, it may assert the interrupt signal to the CPU core and tell CPU core that all the command has been finished. Okay, this is the design requirement of our two-dimensional DMA controller. For next step, we have to figure out the hardware architectures to implement all the features. And we have to partition these features to sub-blocks that we think we can handle and we can code it. Okay, please try to figure out the hardware architecture for these features and try to partition it to sub-blocks. That's all for this section. Thank you.